Okay, so good afternoon, everyone.
Afternoon.
Yeah, so couple of things. So I just got the information that my internet connection, there might be a disruption sometime in the afternoon. So if that happens, like I have an alternate source of internet. So for a brief while, I might, be offline, at the time when I make the switch. So yeah, I would appreciate your patience at that point when you wait. Okay, so that's one. And the other thing is, yeah, I've uploaded another assignment. So yesterday I uploaded one assignment. So that's your second assignment basically. And so that has about 6 questions. So 3 theory and 3 in the programming part. So the number of questions is a little lesser than the previous time because it's your midterms and those are coming up. So I didn't want to burden you too much. And another reason is the programming assignments are a little more involved this time, especially for one of the questions you will have to read up a bit on logistic regression. So maybe you already did it in a machine learning course, I don't know, but anyway, it would help you if you read some of it for the assignment. So that I expect will take some time. So that's why the assignments are this time it's a little short. But in any case, I would encourage you to try out several problems in textbooks at the end of the chapter. So by now you should be going through all the references. So the more problems you solve, you get more comfortable with these with optimization. Okay, so yeah, that's just about some announcements. Okay, so let's begin today's class. So any questions till now? Anything with the assignments or anything in general in the course? It's all okay?
Ma'am, in the second assignment, there is a question. The first question, there's an optional part that says visualize those functions. So visualize
Right.
those functions that it means that the using program, right? Plot the
Yes,
graph.
yes. So I think this was the second assignment, right? So these questions, find the critical points and verify. So you remember in class we did something to this effect, right? We got the critical points and we used these conditions to classify. But an additional check you could do is plot and see whether it tallies with what you get, right? So you get a better idea about the function itself. So that helps. But anyway, that's an optional part. Yeah.
Yes,
Rohit,
ma'am.
that's okay?
Thank you, ma'am.
Okay. All right. Fine. So I guess the rest of you are comfortable. If not, I would urge you to reach out to me if something is not comfortable at any point. Okay. So let's resume our discussion on convex functions and convex sets. So recall that we started defining these kind of sets where any point you take and you connect any 2 points you take and you connect the line between them. All points on the line belong to the set. So such sets are called convex sets, and we saw some examples like geometrically, and maybe some very simple examples we saw here. And we saw that the set of integer points, if you have a polygon and you restrict yourself to the integer points, that's not a convex set. Okay, and then we saw the notion of convex hulls, and then we went on to convex functions. Okay, so we were looking at convex functions through this definition, which said that if you take a function and you take any 2 points, okay, and then you have the line joining the 2 function values, and you take a point here, the corresponding function value as well as the point on the line joining the 2 points, the function lies below this line. So that was the idea behind convex functions. Yes.
Ma'am, here at this particular point, joining the 2 lines, the point, suppose this is lambda fx plus 1 minus lambda fy. So when you projected it on horizontal axis, so how does this point z came here? to be lambda x plus 1 minus lambda times y.
You're asking how this point is also lambda fx plus 1 minus lambda fy?
That is lambda fx plus 1 minus lambda times f of y. That is some point on this line joining fx and fy. So when you projected this particular point on the horizontal axis, so how come this z is equal to this lambda times x plus 1 minus lambda y?
Yeah, exactly. So let me just explain this a little more. So what we are saying is, another way to say that is the fraction over here, like the weights you give on this horizontal line for x and y, the proportion, right? Lambda proportion for x and 1 minus lambda proportion for y. If you if you extend this point vertically upwards to this line, though this is not horizontal, the fraction you allot to f of x and fy is also the same lambda and 1 minus lambda. Okay, so yeah, it's a good point, like why this comes. So this will be clear, like if you zoom in a little bit into the function. So let me just so let me just try to draw only this relevant part. So here this is something like this is x and f of x, okay, and this is y and f of y, right? This is the point. So I'm just taking these 2 points and drawing them here, okay, and so on the x-axis this is x and this is y. So this is the straight line here, right? So this line is actually this one. So this is x and this is y. Okay. On the x-axis, this is x and this is y, and on the y-axis you have fx and fy. Okay. So now the claim is, so this point here, this was lambda x plus 1 minus lambda y. This is the point z. Now the claim is even this point here. This is also, if you take it as vertically upwards, this one, this point is z and lambda fx plus 1 minus lambda fy. Okay, so it's not obvious, right? Why, this is a lambda weight here and 1 minus lambda weight to this point. Why the same proportion comes here for a point which is directly above? So this is, you can show this by using the notion of similar triangles.
Yes, ma'am, got it.
Right, so these two, this triangle, the smaller triangle and the larger one, they are similar. So yeah, you can compute these ratios. So you need to take the ratio of this side to this side versus this side to this whole side. Okay, those ratios are the same. So if you do a simplification there, you will see why this is true. Okay, so that's a good question. I had this question at some point, when I was learning convexity. So that's good. So I hope this is also clear to the rest of you. Right, so, okay. Yeah, so just work this out yourself, you'll see this. Okay, so yeah, coming to this notion of convex functions. So this is what we said, okay, that f of lambda x plus 1 minus lambda y is less than lambda times fx plus 1 minus lambda times fy. Okay, and we saw just a geometric intuition for what this means. Okay, and we finally stopped the class with this theorem, which said that if you're trying to minimize a convex function over a constraint set which is convex, then it turns out that any local minimum here is also a global minimum. Okay, so that's a feature of convex, these kind of convex problems, and we also proved this. Okay, so this is kind of where we stopped in the last class. So I realized I didn't give you any examples of convex sets, particular examples. We saw some figures, but I just want to give you some very commonly used examples of convex sets. So the first example is that of a hyperplane. So this is it's an extension of lines to n dimensions. So it's basically the set of all x such that A transpose x is some value b. Okay, so this is drawn in this manner. So basically you have this, it's a notion of a line itself. So in 2 dimensions, it's a line. So the vector A is something like this. It's normal to this line, so that you will see in a minute what it means. So this is normal to all points on this line. Okay, so in the sense that if you have some point x naught here, and you have a point x, okay, any point on this line. So now this x minus x naught is this vector. So A makes an angle of it's orthogonal to this vector x minus x naught. Okay, so let's just write it here. So A transpose x minus x naught is 0. Okay, so what this means is that A transpose x is exactly same as A transpose x naught for some point x naught, and this is the point with, I mean, this is the value B, and all points on this line, on this plane, are going to have this relation that if you take the transpose with A, you're going to get the same value B. So that's what you mean by a hyperplane. Okay, so this is a convex set, and the proof is quite simple. It goes by the definitions itself. So if you take any two x1 and x2 belonging to this set, so you have this relation that A transpose x1 and A transpose x2 are both B. So if you take a convex combination of these 2 points, that would be this Z. And if you take A transpose of this set, if you multiply it with A transpose, what you're going to get is just, lambda A transpose x1 plus 1 minus lambda A transpose x2. And this, is B, and this also, is B. So that's why the overall, dot product with A also, I mean, for Z also you get B. So that's the proof for why this is a convex set. Okay, so now another related set is half space. Okay, so half space is you take the hyperplane and you take one half, so maybe this half. Okay, so this is the set of all points which lie on one side of the hyperplane. Okay, so basically this shaded region, that is what is the set we are considering now. And this is also a convex set. Okay, so the proof also follows along the same lines. Okay, so I mean, you should be able to show this. Now, another example we've seen before is the notion of Euclidean balls. Okay, so this was the neighborhood, basically to capture the neighborhood concept, we had used the notion of balls. So basically you had a point xc and you looked at all points within some radius r from xc. So this was a case where the norm you used was 2, but in general you could use any norm. And this, yeah, so all points within a radius of r from xc. So this is also a convex set. Okay, so by the geometry, it's of course very clear. So it's basically the inner part of this circle. So you could also use these definitions to prove it, right? So I mean, the proof is quite simple again, because these are two sets two elements of this ball. So you have this relation, the distance from xc is r, and for both of them, and then you take lambda times this one, lambda times x1 plus 1 minus lambda times x2, that is z, and you want to say that this also lies within a distance of r. Okay, so basically it's these 2 points, you take x1 and x2, so any 2 point, and if you draw this line, anything joining this, so this point will also be at a distance of less than r from xc. That's the idea. So so to prove this, I mean, the idea is to use this triangle inequality that we have for norms. Okay, so this should be fairly straightforward. You should try to see that makes sense. Okay, now another set I wanted to just briefly mention to you was the set of positive semi-definite matrices. So this is basically the set of all matrices which are symmetric and also symmetric, and they have this positive semi-definite feature. Okay, and so this is also quite straightforward to prove. Okay, so here all the components of this set S plus are matrices. Okay, so you have A, B in this set. So what it tells you is that these are positive semi-definite. So you have this kind of a relation that's true for every x in Rn. I mean, you have x transpose Ax is greater than 0 and x transpose Bx is greater than or equal to 0. Now, any convex combination you take, lambda A plus 1 minus lambda B, you will have x transpose Cx is this. Okay, it's just expanding along this one. And because lambda is positive, then this whole term is greater than or equal to 0. And similarly, lambda is between 0 and 1, so then this is greater than or equal to 0. Okay, so that's why this is also going to be greater than 0 for all x. Okay, so then you have that C also is positive semi-definite and it will belong to this set. Okay, so yeah. So any questions till this point? So some quick examples that I thought would be good to show. Any questions,
ma'am.
Stella? Okay. So I'm just going through it quickly because I think these are fairly straightforward. But if something is not clear, do stop me. Okay. So now one other feature about these convex problems is that, one thing you saw that all local optima are also global optima. Okay. Now another feature is if you take the set of optimal solutions to this problem, okay, where f is a convex function you're trying to minimize, and over the convex set, the set of optimal solutions, that also is a convex set. Okay, so in short, just to see it visually, so this is a convex function, and the minimum, if there are multiple minima here, so for this case, x1 and x2 are both minima. So now this is going to form a convex set. So anything that you join between x1 and x2, so all points here, this whole interval is going to be it's going to be optimal for this problem. That's what it means. Okay, so it can only have something like a constant in this range, and this is the optimal. Okay, so something like this is not acceptable. So here, this is one minimum, and this is another minimum. Both of them have the same value, same objective, but yeah, something in between this is not optimal, right? Like for example, this is not an optimal point. So this kind of a behavior will not happen for these kind of functions. Okay, so the proof is quite simple. Let's just have a quick look at it. So suppose S is a set of optimal solutions. So what it means is that f of x is less than or equal to x tilde, fx tilde for all x tilde in the set. So this is true because you know that any any local optimum is a global optimum. So you don't have to distinguish between the two for convex problems. So that's what this means. Okay. So now you take x1, x2 in this set. So the claim is that any convex combination of these two is also going to be optimal. Okay, so let's just see what, let's just try to apply the definition itself. So what we have is f of lambda x1 plus 1 minus lambda x2. Okay, so this is the new point that we are taking. So x1 and x2 are in this set of optimal solutions. Now I'm applying the function on this convex combination. So I know that because f is convex, this is going to be less than lambda times f of x1 plus 1 minus lambda times f of x2. Okay, this is just the notion of convexity. And now we know that f of x1 is going to be less than f of x tilde, right, for all x tilde in the set, because x1 is optimal. And similarly, this is also going to be less than f of x tilde. So overall, this quantity is going to be less than lambda times fx tilde plus 1 minus lambda times fx tilde. Okay, so this is just f of x tilde, this quantity. So this is true for every x tilde in the set. So that's why, so what you have just shown is that the new point you take, z, is also going to satisfy this property that f of z is going to be less than or equal to fx tilde for every x tilde in the set. So so z is also going to be an optimal point. Okay, so z also lies in S. Okay, is this clear?
Yes, ma'am.
Okay, what about the others? Rohit, it's clear for Rohit. The rest of you? Yes, okay. Okay, that's good then. So, yeah. So this is about, these are some of the nice features of convexity. Okay, so the thing is that, it has these nice features, but, it's not in general easy to show whether a set is convex or not. Okay, so even identifying whether a problem is convex, sometimes it can be hard. Okay, like whatever I showed you here are like some easier examples, but in complete generality, it may not even be easy to show this, and so that's where there are there's this emphasis on some operations, okay, on some sets, and if you do these operations, you retain convexity. So some convex sets and some operations that you do on them give back convexity. So it's useful to have these. So let me just talk about some of them. So first thing is the intersection of convex sets. This is going to be convex. So you can see this in this example here. So this is a convex set, this circle or ellipse or whatever. Okay, so this one is convex, and then you have this triangle, so that's also convex. Okay, so now the region which is in the common part of both these is this one in red. Okay, so this region is also, the claim is that this is also a convex region. Okay, so that should be straightforward to prove. I mean, you can use these definitions to prove this. Now, an example which gets used, and you will also see this in this course, is this kind of set, where the set of all x where ax is less than or equal to b. So what this means is that you have some m inequalities, okay, in x, and you want all of them to be satisfied simultaneously. So this is a convex region. Okay, so we have seen things like ax equal to b, right? So this is a system of equations. So what we are saying is not ax equal to b, it's ax less than or equal to b. So an intersection of m half spaces. Okay, so that is a convex set. Okay, so now let's look at the union of two convex sets. So S1 union S2, by that we mean that you take all x where x is either in S1 or x is in S2. So S1 and S2 are convex. So what do you think? Is this a convex set?
No, ma'am.
No. Okay, so why?
It could be like a W-shaped function, for example.
Something like a W shaped in the sense like, okay, so something of this form you're seeing.
Yes.
Yeah, so that's right.
Ma'am.
So, but you're talking of functions here, but what we are looking at is sets. Okay,
Yes.
so that will that is a different notion. So then you don't call this a union also, right? So this is not an example for this one. So somebody wanted to answer. Somebody else.
Ma'am, I had one question.
Yes,
That
Viransh.
how did you tell that circle was a set of convex? I mean, circle was a convex set.
This one. So circle, okay, so this, I mean, intuitively speaking, like any 2 points you take here, if you connect the line joining them, that's going to lie in this set, right? So that's going to be true for any 2 points you take. So, okay, I think I understand the confusion. So when I say the circle, I mean like, so here I meant like all the, okay, my drawing skills are bad. So what I meant is everything inside the circle, okay, not the periphery alone. Okay, and similarly for the polygon, I meant everything inside the polygon. So if you take the circle periphery alone, that is not a convex set. Okay. So Viransh, was that the confusion?
Yes, ma'am. Yes.
Okay. Yeah, thanks for asking this. Yeah. So, okay. So
just like that
union,
circle and
right?
triangle thing, the point joining the tip of the triangle to the circle, that does not lie in that area. So
yeah, something like, okay, you're telling of the same example, right? You have this circle and you have this triangle. Yeah, correct. So something like this doesn't lie.
yes,
Yeah, that's exactly the idea. So this is a convex set, and this is a convex set. But if you take the union, you're going to get this whole region. So if you take these 2 points, the line joining them, that will not lie in the set. Okay. So that's about this. You can see simpler examples in one dimension. So the interval, say something like 0, 1, union something like 2, 3. Okay, so this is just a one-dimensional example. So you have 0, 1 and 2, 3. So this region is convex, this region is convex, but now if you take them together, you will get this space which doesn't belong to the set, so it's not convex. Okay, now another operation is what is called the Minkowski Sum. Okay, so I don't know if my pronunciation is right, but anyway, so it's a sum of two convex sets defined in this manner. So you have S1 and S2. So these two should be compatible in some sense. In the sense you can't have S1 in Rn and S2 in R. Okay, so for instance, that's not okay. So both are in the same broad region, and you take this sum as x1 plus x2. Okay, sum of any two vectors which lie in S1 and S2, and you call this a new set S. So this set is convex if both these S1 and S2 are also convex. Okay, so this you can also prove it using the, just by the definitions. So I urge you to, go back and just try for your own satisfaction that these are indeed convex. Okay, so so these are some operations. Of course, there are a lot more operations, and I've not covered a detailed set of these operations. Primarily because I want to focus on some other aspects as well. But and especially this is not a fully it's not fully focused on convex optimization. So that's the main reason. But you should go back and read the textbook for these exhaustive set of operations, and Boyd is the standard reference for for this convexity. So you can find, it's there in great detail. Okay, so now I want to move on and talk about convex functions. Yes.
When you said sum of two convex sets, it should be like the union of convex set, right? Not the sum.
Yeah, so union of two convex set is something like this, right? X in S, when you take all points in S1 and all points in S2, and you club them and make them one set. So that is what is union. So here this operation is a slightly different one. It's not what is union. So what this means is that if you have some Z which lies in S1, then if you have some Z which lies in this set S, then you can represent Z as some x1 plus x2. So this is actually a plus operation. You take the vector, so x1 is a vector and x2 is going to be a vector. So you take the element-wise summation, and the claim is if you have Z in this S, you can write Z in turn as the sum of two elements, one in S1 and one in S2. Okay, so if you have a set like this, so this kind of a set is called the Minkowski sum of S1 and S2. Okay, so this is different from the set union. Okay, so the claim is this set is convex if both these S1 and S2 are themselves convex. Okay. So,
ma'am, so it is more like closure property, right?
By closure property, what do you mean?
Like if you're like x1 and x2, like this is in a convex set, then x1 plus s2 is like in the combine of both these sets.
Yeah, so for convexity, you have this convex combination. So here you are just taking, it's just an addition. So in that sense, yes, it's the similar operation that you do when you did convexity. Like lambda x1 plus 1 minus lambda x2, right? You had that operation. So this operation is similar to that. It's exactly the same, but without those weights. Okay.
Okay. Yes.
Yeah. So that's why, so that's why you need S1 and S2 to be compatible in some sense, right? You cannot add some vectors which are in, different spaces. So, right. Yeah. Okay. So, okay. So are there any other questions till this point?
Ma'am, is union then, does union make sense when they are in two different spaces?
Yeah, so union also, yeah, they have to be in the same space, but it's a little loose in that sense, because you can have something like S1 could be something on the real line, okay, and S2 could be like the whole two-dimensional set. So if you can view X1 as something on the x-axis and S2 as something, like in the joint space. So in that sense, it's a little loose. You could do something like that. But of course, then in that case, you should say S1 is a two-dimensional thing where, X1 and 0, the y coordinate is something like 0. But yeah, your point is valid. So in general, even when you take union, ideally you should ensure that they are in the same subset. Okay, so they are in the same space, or at least when you take a union, that new space that you get, it's a valid space, right? So that is something you should take care of, right? Okay. So that's clear.
Yes, ma'am. I was just thinking because even there also we need to take this sum, right? Lambda x1 plus 1
Yes.
minus lambda x2.
Yes, true. So yeah, that's a valid point actually. Yeah. So yeah, thanks Siddharth for asking this. So okay. So yeah. So any other questions till this point? It's all fine.
Yes, ma'am.
Okay. So let me just move on. So I wanted to talk to you a little bit now about convex functions. And there's this inequality called Jensen's inequality, which is defined for convex functions, and it keeps getting used in many places. Okay, so you probably saw this in the machine learning course, and yeah, but anyway, I'll just explain it for those of you who, I know many of you wouldn't be taking the course, machine learning course. So let me just talk to you about this. So it has a lot of applications in machine learning, and even in different fields like industrial engineering and so on. Okay, so just some details on this. So remember, like so far we were looking at convex sets in this class. So now we are just taking a shift to convex functions, where there was this function f. And what you said was a convex function is that you take any convex combination. So we discussed this in 2 dimensions, right? So we had something like this, f of lambda x1 plus 1 minus lambda times x2 f of x1 plus 1 minus lambda fx2. Okay, and this is true for all x1, x2 on which, in the domain of the function f. Okay, so now if you generalize this idea to, k points, what you're going to get is just the summation, okay, of lambda xi, and where these lambdas have this relation. Okay, so they all sum to 1 and they're all greater than 0. Greater than or equal to 0. So if you take this, so this is a convex combination of the x's, and if you take the function value of them, of this convex combination, this will lie less than, taking each of the xi's, taking the function value and scaling it by a lambda factor. Okay, so this is just the generalization of this 2-dimensional definition. So, one alternate view of this expression is that you could bring in some notion of probability distributions here. So the reason is that you see that all these lambda is summed to 1 and they're all greater than or equal to 0. Okay, so you can interpret these as a random variable. So something like this, right? A random variable x, which takes a value xi with probability lambda I. Okay, so you can define something like this, a random variable x, such that it takes k values, so x1, x2, and so on up to xk. So these are the support points. So these are the outcomes. Okay, so something like you throw a dice, so there's 6 points, right? So yeah, these outcomes are there, and each of them has a probability lambda I. Okay, so this is a random variable. Okay, and what this is saying, the summation lambda I xi. So lambda is the probability, and you take all the outcomes and you take summation lambda xi. So this is just the expectation of this random variable x. Okay. I guess you all have done a probability course before, right? So this, I hope this is clear.
Yes, ma'am.
Okay. So what about the undergrads? This you guys are third year, so you must have done an undergrad course last time, right?
Yes, ma'am.
Okay.
Yes, ma'am.
So, okay, good. So I hope this notion is clear. So you have this expectation of x. You just take each of the points, the outcomes, and multiply it with its probability. So that gives you expected value of x. And so what you have on this side, so the left-hand side of this is just f of e of x. Okay. And on this side, what you have is you're taking f of x, okay, for all these points, and then you're taking a convex combination, right? So this is as if you are defining a new random variable. So y is f of x, so where x is this one, and y is f of x. And here what you're doing is just, this is just the expected value of y. Okay, what you have on this side is just expected value of y. So what this is telling you, the convexity definition tells you that f of e of x, which was on the left hand side, this is less than expected value of f of x. So expected value of y, which is just f of x. Okay. So this is what is called the Jensen's inequality. It's just convexity. But one thing is, this notion you can generalize it to continuous spaces also. So for instance, here we took it as, like some k points we took. So if you want to generalize this to, continuous probability distributions, what you would do is, instead of the summation, you would have this integral, right? So something like this, f of integral lambda x times x dx. Okay, so this is an integral over x. Okay, so that should be clear. Okay, and this is less than summation. So here, instead of the summation, you are going to have an integral, and this is going to be lambda x f of x dx. Okay, so this is exactly the expectations in continuous spaces. So this is what is the Jensen's inequality. Okay, so any questions on this?
No questions, ma'am.
Okay, so Rohit is clear, and the others, what about?
Ma'am, is there any intuition behind this inequality?
So yeah, I mean the intuition, it's just about the convexity. I mean the convexity of the function, basically. It's just exactly the same thing. Okay, it's just extending this to larger spaces and stuff. But yeah, apart from this, I think the intuition just comes from the convexity. Okay, I don't think there's any other intuition here. Okay, so but are you finding this hard to follow, like when we make the switch from here to the case of expectations? Is there something which is troubling you, which is, I mean, with these steps?
No, ma'am. No, ma'am. It's fine. I was just asking anyways.
Okay. So, yeah. So usually, like, to remember this, it's quite hard, right? I mean, like I always used to, find it hard, like when I say f of expectations and expectation of f, which way should I take? And, is there something to, mug up? So yeah, if you know this, expression, then this just follows as a result of that. So I just wanted to make that point here. Okay. So now, so this is about convex functions, and on the other hand, if you have concave functions, this kind of reverses. Okay. So remember, we have, what is a concave function? When minus f is convex, that's when you say f is concave. Okay, so when minus f is convex, you say f is concave. Okay, so so all these inequalities are just going to reverse, and for concave functions, this is just going to be f of e of x is greater than or equal to expected value of f of x if f is concave. Okay. So yeah, these are some things, and I can, I mean, this kind of relates a bit to some research that I've been doing. So, in many fields, you try to find, when you're trying to do an optimization problem over the space of probability distributions. Okay, in the sense you want to find a joint distribution which maximizes some expectation. So then, what you can use is this one. I mean, what you have, this function of this expectation, that gives you a lower bound. Okay, that gives you some kind of a baseline. You take any distribution in that class, and if you compute this quantity, that gives you a baseline. So that is something which people use a lot. Okay, so anyway, so that was just a diversion. So it's I just got carried away by this, but anyway. So I just wanted to mention this because this gets used a lot. So now moving on, let's look at some other characterizations of convex functions. So we saw one of them, right? The f of lambda x plus 1 minus lambda x, and lambda y, and you see that this is less than lambda f x plus 1 minus lambda f y. Now, there are several alternate characterizations. So one of them is, if you take a differentiable function, which is also convex, and what it means is that, if f is a convex function, then its domain, of course, has to be a convex set. And you also have this kind of a relation, okay, that has to be true. Okay, so let's just see what this means. Okay, so so this one, this fx plus y minus x transpose grad fx. So recall that this is the first order Taylor series expansion around x. Okay, so this is the function f in red, and I'm taking a point x. Okay, and I'm drawing the first order approximation at this point. Okay, so what this condition is telling you is that f of y, the function, is always going to lie above its first order approximation. Okay, so for any y you take, so if you fix an x and you draw the first order approximation, now for any point, any other point, so y is somewhere else. So if you take the function value, it's going to lie above this first order approximation. Okay, so that's what this means, and this is true for any point if you vary x somewhere else. So something here, if you take this as your x, the first order approximation is going to be something like, something like this. Okay, so pardon my drawing again. This tablet is quite crazy. So this is the first order approximation, and the function will lie above this line. Okay, so that's the idea behind this characterization. So is the statement of this thing clear? I mean, we'll show a proof of it, but is the statement clear to you?
Yes, ma'am.
Okay. Rohit says it's clear. What about the others? None of the girls are responding today. What's up? Devyani, Bhavna, Tushar, it's clear? Good.
Yes, I'm clear.
Okay. What about others? Nitish says it's clear. Okay. Okay. All right. So please stop me, okay, if this is not clear. Some notions need more explanation. I'll be happy to do that. Okay, so
That equation of line, that fx plus y minus x transpose grad fx, did we do that in like a previous class?
So this one, we have seen it at different points. Like this is the Taylor series expansion of f around x, right? So this is the first order Taylor series approximation.
Right? Sorry. Yes, ma'am.
Yeah. So I'm glad you recognize this. So that's good. Okay, so this is a statement that the function lies above the first order approximation. Okay, so let's just see a proof for this. And it's always like for convex functions, if this is the case, for concave, you have the other way around. Okay, so there you'll have the first order approximation lies above the function. Okay, so that would be something like this. Okay, so this is the function and this is x, and yeah, so this is the line which approximates the function at x, and that lies above the function. Okay, so let's just see a proof of this. So, so this is true both ways. Okay, so if you're given a convex function, then this is true. And suppose you are given that this statement is true and the domain is a convex set, then it's true that f is a convex function. Okay, so both ways it's true, and so the proof will have both directions. So first, let us assume that f is given to be convex. Okay, and so take any xy in the domain. So first thing is the domain has to be a convex set. Okay, because otherwise you cannot even define something like lambda x plus 1 minus lambda y. Okay, if this has to, if the function, if this is a valid point, then this has to be in the domain. Otherwise, you can't even compute the function value here. Okay, so that part is straightforward. Now let's just take the value of the function at this new convex combination. So I'll just write it in a slightly different way. So you recall that this is another way to write the same convex combination. So this is just nothing but 1. So this is 1 minus t times x plus t times y. Okay, so I'm just writing it as to give the idea of x plus t times this vector y minus x. Okay. So this is going to be just less than 1 minus t times fx plus t times fy, because you're given that the function is convex. Okay, now if you divide this by t on both sides, okay, so it just boils down to this. So the left hand side is just this expression fx plus t times y minus x by t, and on the right hand side this t goes out, so you have f of y plus 1 minus t by t times fx. Okay. And so this is in turn what? So fy, so it's just some algebraic manipulations here. So where you write 1 minus t by t. So this is just 1 by t times fx minus fx. Okay, so now rearranging this, f of y is just fx plus this term minus 1 by t fx. So that's what comes here. So this is just this term and this term 1 by t times fx. Okay, together gives you this. So now yeah, it's our usual operation, take the limit as t goes to 0. Okay, so because you want something as in terms of the grad of fx, so that's why this limit t goes to 0 comes. So if you take the limit as t goes to 0, what you're going to get here, this expression, is just going to be the directional derivative, right? So this is just the directional derivative that we defined in the preliminaries. So that is the component of some d in the direction of grad fx. So it's also computed this way: the limit as t goes to 0, fx plus td minus fx by t. Okay, so it's as if this y minus x is the direction t. Okay, sorry, the direction d. Okay, so yeah, so it's just a substitution of this directional derivative, and that gives you this whole expression is just the directional derivative in the direction y minus x. Okay, and so bringing both these together, that's exactly what the first order condition is. Okay, so yeah, so it's a bit of algebra, but yeah, it's a straightforward application of whatever you saw earlier with the directional derivatives. So any questions on this part? Okay, am I speaking to myself?
No questions, ma'am.
No questions. Okay. Okay. I don't know why you're all very quiet today, but yeah. Please ask, okay, if something is not clear. Okay, this is clear, good. Okay, so we're almost at the end of time, but let me just finish the other part also, which is, I assure you, it's a little more straightforward. Okay, so So the other way is that suppose the domain of f is convex, and suppose for all x and y you have this is true. Okay, so now the idea is to show that f is a convex function. Okay, so the way you do this is you have these xy points for which this relation is true. So this is our favorite operation. You take the convex combination of these points, lambda x plus 1 minus lambda y. Now you apply this expression, this kind of a relation for between the pairs y and z and between the pairs x and z. Okay, so that gives you these two inequalities. F of y is going to be greater than or equal to f set plus y minus z transpose grad f. So this is just substituting these here. Okay, now you same thing for x, and you multiply each of these equations. Okay, so this one times 1 minus lambda and this times lambda. So what are you going to get? Can somebody tell me? So left hand side is what? So you take 1 minus lambda times this equation and sum it up with lambda times this equation. So left hand side will give you lambda fx plus 1 minus lambda fy, right?
Yes, ma'am.
Okay, and what is the right hand side?
Fz plus.
Yeah, so lambda times fz plus 1 minus lambda times fz, that will give you fz plus
1 plus lambda x minus z dash.
Yes, so lambda x, I'll just write it as lambda x minus lambda z transpose grad f at z plus 1 minus lambda, right, 1 minus lambda times y minus 1 minus lambda times z times this transpose grad f z. Okay, so now if you take these two together, so what these two terms together is this one and this one. Okay, so what this gives you is, so lambda x plus 1 minus lambda y. Okay, so that is this term and this term. And what are the remaining terms? So I want to write this as this transpose grad f z. Okay, so grad f z remains. I'm collecting these two. So then you have minus lambda z minus 1 minus lambda z, right? So this is just minus z. So lambda z plus 1 minus lambda z is z, and with a negative term here. So this is minus z. And recall that z is lambda x plus 1 minus lambda y. So this is also z. Okay, so this term is just going to vanish. So this whole term just vanishes. So you'll get 0 transpose grad f z. So you're left with just this. Okay, so remember this is exactly our definition of convexity, right? So
Yes.
yeah, so this is true for any 2 points you take, x and y. Okay, so is this clear? Any questions further on?
Clear, ma'am.
Okay, so Rohit, is this clear? The rest of you? Ravna is clear? Okay. It's clear? Okay.
Ma'am,
Yes, Siddharth.
when is the case when we explicitly say that the domain is convex?
Yeah,
what
so
is the difference between function being convex and when we are explicitly saying that domain is convex?
Okay, so the domain of this function, this is a set, right? So this is a set on which you define the function, right? So you understand domain? Do you know the definitions of domain?
Yes, ma'am. I know the definition. I was just curious if how are we saying that domain is always domain of a convex function is always?
Oh, okay. You're asking like that. So that is just because, when you say that f is a convex function, you inherently, you implicitly are assuming that the domain is a convex set. Okay, because in the definitions you have this convex combination, right, of any 2 points. Now, if that convex combination of those 2 points is such that, it doesn't lie in this domain, so then you can't even apply the function on that point, right? So that's the reason why, the domain is always, it has to be a convex set. In fact, in the definitions of the convex set itself, it is implicit. Okay, so this is convex set. And see, so if you have every xy in the domain F, and if domain of F is a convex set, so that has to be there as such for the function to be convex. Okay, because if you cannot take the function of this, then it doesn't make sense to even do this operation, right? So yeah, so in some sense, maybe it comes so naturally that sometimes it seems like, okay, why do we have to state it specifically? But I think it's just done to be like more precise and stuff like that. Okay, so that we don't forget that the domain has to be a convex set. Okay, that's just the idea behind writing it explicitly. Okay. So does that clarify?
Yes, ma'am.
Okay. So any other questions till this point? So we did the first order, right? Yeah. Okay. So yeah, I don't know if I can do one more thing, which is a second order conditions. And I think that would be a logical point to stop here. I mean, we are not going to prove this, but it's just something that you have all seen before. So if a function is twice differentiable, then, when we say f is convex, it's also equivalent to saying that, of course, the domain is convex and the Hessian, okay, the second order derivative or the Hessian is positive semi-definite at every point. Okay, so this is another characterization of convex functions, and it's also both ways. So what this is saying is just that, the function is increasing at every point. I mean, if you look at the slope is increasing, not the function is increasing. So something like this. Okay, so if you take the function is in this way, now the slope at every point, if you take this is the slope at this point. Now, if you come here, this is the slope is something like this, right? And if you see the slope, I mean, it's just very loosely put, but this is increasing at every point. I mean, here it's a negative slope, and this is less negative, and finally when you come here, the slope is 0, and as you go further on, the slope is just increasing. Now here, that's the idea behind saying that the Hessian is positive semi-definite at every point. Okay, so in a one-dimensional case, it just boils down to saying that the second order differential is greater than or equal to 0. Okay, throughout the domain. So this is also an alternate characterization for convex functions, and it's both ways. So if it's convex, then you have that the Hessian is positive semi-definite, and other way also, if the Hessian is positive semi-definite at every point, then the function is a convex function. Okay, so these are some of the things which will be useful to show that a function is convex. So I will look at some of the examples maybe in the next class. So yeah, I think this would be a logical point to stop. But are there any questions so far?
No, ma'am.
Okay. Okay. So in that case, yeah, I think that will be it for today. So if there's anything, I'll just hang back to answer any questions. So thanks a lot for making it here, and have a good weekend. I'll see you on Tuesday.
Thank you, ma'am.
Siddharth, are you asking something? I think your mic is off.
Ma'am, it must be on my mistake. It was off on me. I have no questions, ma'am.
Okay, Siddharth.
Thank you, ma'am.
Yeah.
Thank you, ma'am.